Hello everyone. So in this video of chapter coordination compounds, I'll be talking about VBT and the formation of some complexes on the basis of VBT theory. Theory of bonding in complexes. The metal ligand bonding in coordination compound has been described by two theories. Number one is Valence Bond theory and number two is crystal field theory. First we will talk about Valence Bond theory. The hybridized state is a theoretical step that describes how complexes are formed. VBT is the theory which is based on hybridization, and the hybrid orbitals neither exist and they are not even detected spectroscopically. And the steps involved in describing bonding in coordination compound are as follows according to VBT. Number one is metal ion provide vacant d orbital for the formation of coordination bond with ligands. Vacant d orbital along with s and p orbitals of metal ion will take part in hybridization. Another point is the number of vacant hybrid orbitals formed is equal to the number of ligand donor atoms surrounding the metal ion, which equal to its coordination number of metal. Means if 6 pairs of electrons are coming from ligand to metal ion, then 6 orbital of metal will undergo hybridization. Then overlapping between the vacant orbital of the metal and filled orbital of ligands lead to the formation of metal ligand coordination bond. Next point is the hybrid orbitals used by the metal ion point in the direction of the ligand. Then the n-1d or nd orbital used in hybridization allow the complexes to be classified as number 1 outer orbital and number 2 inner orbital complexes. If for hybridization outer orbital complex nd orbital are used, whereas in the inner orbital complexes n-1 d orbital are used. Types of hybridization decide the structure of complex. For example, if the type of hybridization is D2sp3, so the structure would be octahedral. Now we'll be talking about some complex formation on the basis of VBT. Like octahedral complex, and first complex we are talking about here is hexaamine cobalt 3 ion. First step is we need to calculate oxidation state of cobalt here. Its oxidation state would be +3, and then we will draw the orbital diagram of cobalt +3 ion. So here is the orbital diagram of cobalt 3+ ion, where we will see vacant 4s and 4p orbitals and 3d is containing 6 electrons. Here we are seeing in this ion the number of ligands are 6 in number. That means 6 electron pairs are coming to the cobalt. So there should be 6 vacant orbitals of cobalt ion. Since the complex is low spin, then the pairing of unpaired electron present in 3d will take place prior to hybridization. So now after pairing, this would be the structure of 3d. We'll be having 2 vacant orbitals in 3d. 1 is in 4s and 3 in 4p. Since 6 electron pairs are coming, we will be require 6 orbitals, and these 6 orbitals would be 2 orbitals from 3d, 1 from 4s and 3 from 4p. So these 6 orbitals will undergo hybridization, and type of hybridization would be D2sp3. Here n-1d orbital participate, that is why it is inner orbital complex, and it is low spin complex also. Then after coming of the electron pairs of ligand, which is shown as pink electrons, this would be the structure, and this would be the arrangement of amines, 6 amines around the cobalt bonded with coordination bond. Since all electrons are paired in this orbital diagram, so the complex is diamagnetic. Let's take another example, and another example is hexafluorocobaltate ion with oxidation state 3. Here this complex is high spin. Oxidation state of cobalt is +3. If it is having +3 oxidation state, so this would be the orbital diagram of cobalt 3 plus ion. 6 fluoride ion are coming, that means we would require 6 vacant orbitals. Since complex is high spin, that means the pairing of electron will not take place prior to hybridization. So this electronic arrangement in 3D would remain same. So 6 orbitals available for hybridization would be 4s, 3 orbitals from 4p and 2 from 4d. These 6 orbitals will undergo hybridization, and type of hybridization would be sp3d2. Again, shape would be octahedral only, and in this way the electrons of ligand would be shown in the orbital diagram. And here in this orbital diagram we are seeing there are 4 unpaired electrons. So the complex is octahedral because hybridization is sp3d2. 4 unpaired electrons, that is why it is paramagnetic, and this would be the structure of the complex ion formed. Now let's talk about tetrahedral complex, and the example is tetrachloronickel 2 ion. Oxidation state of nickel is +2. This is the electronic arrangement of nickel ion in 3D. Since the complex is high spin, there would be no pairing, and 4 ligands electron or 4 pair of electrons are coming. That means we require 4 vacant orbitals. So 1 orbital of 4s and 3 orbitals of 4p will undergo hybridization. So the 4sp3 hybrid orbital of nickel ion will overlap with 4 orbitals of chloride ion. In this way the ligand's electron will be arranged, and the hybridization would be sp3, shape tetrahedral, and since we are seeing the unpaired electron in 3D, so it is paramagnetic. Next is square planar complex. In square planar complex we will take example tetracyanonickelate 2 ion. Here it is low spin complex. After writing electronic orbital diagram of nickel ion, we would be finding this is the 3D arrangement of electrons. It has one empty 4s and empty 4p orbitals also. Prior to hybridization, there would be pairing of electron because it is low spin complex. So after pairing, this would be the arrangement of electrons in 3D, and orbitals available for hybridization would be 1 orbital from 3D, 1 from 4s and 2 from 4p. So the hybridization would be dsp2. Since 4 pairs of electrons are coming from 4 monodentate cyanoligand, vacant orbital would be 4 in number. So we'll be seeing the type of hybridization would be dsp2. Since there is no unpaired electron, this is diamagnetic, and the shape is square planar, and this would be the geometry of the complex formed. So in this way we used to show the structure of the complexes. Now Limitations of VBT. VBT did not explain the high spin and low spin nature of the complexes. It did not explain the strong and weak field nature of ligands. It cannot distinguish in between two. It does not provide any explanation for the color of coordination compounds. And the structure of complexes predicted from VBT would not always match necessarily with those determined by the experiments. And to overcome this difficulty, which is arise due to VBT, crystal field theory has been proposed, which is widely accepted.